Okay, the Chapter 7 starts off with solenoid valves. Valves can push water, they can have oil go through them, they can have air go through them. I have some coil that turns it on. Normally a solenoid valve is going to be on or it's going to be off. It's not a in-between throttle type valve. The mechanical guys are normally in charge of the mechanical part of the valve. You as a technician would be in charge of the electrical part of the valve. So I see that I have some closing, I have some coil, I have something I'm pulling up and down, and it's hooked on to a pilot valve and a piston that sits in the enclosure that goes up and down. I have some valve disc that the plunger thingy goes and hooks onto. Depending on what pressure I am will depend on whether or not my liquid has to be on top of the valve or underneath the valve. So at higher pressures, we would expect the pressure to be on top of the valve so I can open it. If I was underneath the valve with high pressure, I could actually push it open. That wouldn't be good. This is a three-way solenoid valve. So the solenoid turns on, the solenoid turns off, and so this is the de-energized position. My oil, and this would be oil basically, so my oil's coming into port 2, doing something, making a piston move, going out through port 3, and then back to a return place. When the solenoid happens, this guy switches to there, he switches to here, and I end up going the other way. Normally solenoid valves that deal with high pressure fluids will have a pilot valve associated with them because they're difficult to move. And so you wouldn't use electricity to move the main valve. You'd use a pilot valve to move the main valve. But again, the solenoid part is something that we'll do there. And we have a hydraulic lab sitting over in the diesel place. Maybe we'll go over there and play with it. If we do, we have to take a lot of rags so that we can wipe ourselves off. Now I'm seeing that I'm using some inlet coming in. I'm only using 15-pound air to push on a diaphragm to open some valve going into the pipe. 15-pound air, that doesn't seem like a lot, but if I have something that's a square foot of area, that's 144 square feet times 15, that's a lot of pounds. I couldn't push back on that. That's more pressure than I can handle. When the valve goes the other way, then I come back and I exhaust. I change direction and I exhaust back to either atmosphere or the air. So here's a guy that is a variable position valve. I have a handle on it so I can go down there and change its position manually if I wanted to, but I'm using air to move it back and forth, and I can have it in some, and that's my valve sitting right there. Normally it would be used for air handling. So if I want to cut back some air going upstairs to heat the upstairs of the house or something, I could have some. No, I wouldn't do that. That'd be way too expensive, right? So I'd have to have some industrial application for something like that in order to do that. And then I'd have some position indication on it so that I know what position it's in. That position might come back, so I could use it as a feedback signal. This is another one. I'm doing the same thing. I'm using air again to position a valve. Now I'm seeing that I can have a place where I can tell what the valve position is in, open and shut. So as I move back and forth between my open and shut position, I go back and forth and have some knowledge of that. And then I also have a way to feedback that to the control panel, to some control room someplace, telling me the position of my valve. A lot of springs, a lot of other things. In general, you're the electrical guy, you don't have to worry about it. But someday, the mechanical guy won't be there and you'll have to say, okay, I'll take it apart. When you do that, take notes. You know, that's all you need to do. So here we have a damper situation where I have a motor changing the damper. So as the motor moves, I bring up this lever, which is going to change the damper and how I flow. So in the welding lab, we have a 10 horsepower motor providing ventilation to the welding lab. When we turned that on originally in Dodge Hall, it sucked a vacuum on the building. You could not open the doors to get into Dodge Hall because it sucked that much of a vacuum on the building. It doesn't take much. I mean, a door is several hundred square inches, right? Several thousand square inches. And so if you only have a half-pound difference, then there's 1,000 pounds of pressure holding the door in, right? And you can't get it open. So we threw in a damper just above the parts room to the outside. And we open up that damper before we turn on the fan. So we bring in air from the outside to replenish the air we're sending to the outside by the ventilation fan. And now now we don't have a vacuum on the building anymore when we turn it on. When we turn it on, because the motor is going to take some time to open the damper, we have a 2-minute delay between the time we hit the on button and the time the motor turns on. And that 2-minute delay is to give the damper time enough to open. We don't have a switch on the damper saying that it is open. So if the motor is broken and the damper doesn't open, then that's a different issue. Now we're going to draw a vacuum on the building again, and it takes some real guy to open it. You know, not somebody like me, because I don't have the right muscular tone. This is a 3-way valve. I can have the water coming that way, or I can have the water going that way. So depending on the position of the valve, I can have 2 sources of water coming in. Let's say I was trying to make paint, and today I'm making my pastel colors, and I'm putting the whites in, and tomorrow I'm making my darker colors, and I need a different color paint. That's what I would do. I'd have some valve like that would switch between my paints. This is a motor-driven 3-way valve, so now I've got some motor-driven means you guys, right? So if it's a motor, that's you. If it's a valve, that's the mechanical guy, but motor is you. So I got some motor that's going to turn and drive the piston up and down in the valve. These are heating elements, and in general, we probably don't recognize too many of them. But this is a heater that would go in and would hook wires up to. That'd be similar to what you have in your hot water heater, assuming that it's not oil or gas. Mine's gas at home, so it wouldn't happen that way. So these are all heater things. Something you'd wrap around a pipe so it doesn't freeze. So in my house in Connecticut, I should wrap some of that around the pipes that are close to the outside, because they freeze every winter. Except those winters when I blow the water out of the system. How do you blow the water out of the system at the house? If you wanted to take all your water out, you know how to do that? Air pressure? You have a 100-pound air compressor in the house that you can just use willy-nilly?
Why not?
All right, so how are you gonna do that? All right, so there's the house. Does the house have a basement? Okay, the house has a basement. Where's the hot water heater? There's the hot water heater. What does the hot water heater have on it?
Water.
A faucet. Where's the faucet? High or low? On the bottom.
bottom.
So I got a faucet low, right? So if I go and I take my garden hose and hook it up to the faucet low and take it out of the basement and lower it to something outside at street level that's that's lower than that, right? And then I turn on it. When I open this valve, what's going to happen?
It's going to spoil.
I'm going to have water flowing, right? Because I have water pressure in the house. So I turn off the pump. Boom. Do I still have water coming out?
Yeah.
Yeah, I still do. And now I go upstairs, and here's the kitchen, and I open the valve. What's going to happen? Open the cold water and hot water valve. What's going to happen? air is going to get in, and the water leaving here is going to suck all the water out of those pipes. So I let that happen for a little while. Then I come over to how many bathrooms do I have?
3.
3 bathrooms. Okay, so I go to the bathroom upstairs and I open it up. It sucks the water out of those pipes. I go to the second one upstairs. It sucks them out of those. I come here. I sucks them out of those. I then allow the guy that's the highest to be open. I shut these other guys down until I have no water flow. At which point I've used the vacuum of the hot water heater to suck the pipes dry. Okay, did I get them all? No. There's still the hose that goes outside, right? So someplace in the process I had to open the guy on the outside to suck the water out of him too, and then close him off. And so yes, if my house was equipped with 100-pound air, I could use that, right? What am I going to do with the you guys here in the drains? What am I going to do with the toilet over here and the water sitting in the toilet? What am I going to do with that? Well, I've already turned the water off of there. I'm going to dump antifreeze down there. That's what I'm going to do. So I put antifreeze in all the U piping that I have. Each of my sinks have a U on it. I dump antifreeze down it. I dump antifreeze down the pipe that the washing machine's on too. And then I go away and then come back in the summer. And everything's fine. If I don't do that, boy, am I hosed. All right, so these are heater things that can be used to do all kinds of different stuff. Okay, well, I want to condition something, whatever it is. So I got some signal coming from, I got some light detecting device here. That's looks like a temperature thing. And I'm going to use a operational amplifier, so I have some voltage out that's high enough and some current, some power coming out of it, so I can actually use it in my circuit. So normally my sensors aren't going to give that big of a signal for me to use anywhere by themselves. So in our PowerFlex 40, we had 0 to 10 volt voltage control of the frequency. That's great over 10 feet. That's great over 20 feet. That's not so wonderful over 100 feet. And then I had the 4 milliamps to 20 milliamps analog control that I made you guys do. That's something you'd want to use to push the current down a wire 500 feet. So in your plan application, the 4 milliamp to 20 milliamp control signal would be your normal control signal being emitted by something out there in the plant, some analog piece of equipment. And if it's not, then you'd make it that way, and then you'd use it. You'd use it in your control system. You try to stay away from the voltages because voltages will depend on the wire. And if the wire's too long, that's not good. Somebody goes and tightens a wire into some place and throws a wire nut on it. The resistance changes, the voltages change, and you could be hosed. So I use an operational amplifier, and this is a voltage follower type thing. But I still have some gain because I have an RF there, right? So I have some gain on that guy. So I can gain it, I can add some power, I can be there. This is a resistance temperature bridge. So I throw in a bridge circuit, and on one end of the bridge circuit I have something that changes resistance with temperature. So in my nuclear power plant, I've got 20 of these guys stuck in the core in different locations. I don't really care what my core temperature is when the main coolant pumps are running, because I know what it is. Whatever the temperature of the water is, that's what it's going to be. When I turn off flow, I'm going to want to know that my core isn't melting down. So I measure the resistance of that resistance temperature guy, and then read it on a chart and say, oh, that resistance is 130 degrees. Good, I'm not boiling yet. or whatever it might be. I put it in a bridge circuit, so now I can have some voltage in, and now I can measure the voltage out across that bridge circuit, use a operational amplifier to add some power to it so I can get it down the line, and then I can use it. Now I can use it on a meter itself to read the meter directly, or a digital piece of equipment to tell me what the temperature is actually reading. These wires are short. They're in my cabinet. They're very close to each other. This guy might be 500 feet away. So he's sensing something a long ways away, sending the wires back. I'm doing it again. What's the difference? 3 wires are hooked up and 4 wires are hooked up. Yeah, I really don't see any difference there. It's just that I brought in a wire. I brought a wire into where the sensor is instead of the wire into the bridge. I would probably rather do it in a 3-wire terminal than a 4-wire terminal, because that looks like too much copper. It would cost me more to hook up. Now, your resistance temperature guys have curves associated with it. Okay, so when I look to see how the ohms change per degree, I'm going to have to find the curve of the instrument that I'm working on, or it's already installed, hooked up to my meter, I don't care. Both cases could be the case. But I have different types of things, so depending on what I make the material out of, I have S, J, K, and E type temperature. These are thermocouples in this case, and what a thermocouple does, I take dissimilar metals, weld them together, and they give me a voltage, is what I do. And depending on what I make the material out of will depend on the slope of the curve for voltage versus temperature. Now, that's not a whole lot of volts, right? At 1,000 degrees, I'm getting all of 400 millivolts. That doesn't seem like a lot, does it? No. But if I had an application, let's say I'm going to put a satellite up in orbit, and I was going to use spent nuclear fuel as the source of the heat, I could put 1,000 of these things in that spent nuclear fuel spot, and maybe it heats up to 500 degrees, and each of them's giving me maybe 20 millivolts. Well, if I have 1,000 of them, then I got 20 volts of power pretty consistently coming from that spent nuclear fuel, lasting for the next 1,000 years. That's a pretty good deal, right? Yeah, pretty much. So in the there's a I forget the space science fiction shows that we had, but we had one with a high temperature reactor. Now, normally we don't like our nuclear reactors to be high temperature. 480 degrees is nice. Nothing's melting there. Isn't that wonderful? But we had several reactors that we built that were hydrogen-cooled reactors. And we ran them at 5,000 degrees and used the hydrogen to take away the heat and make the turbines run. Clearly, when I do an outer space type thing, I don't have a heat sink to throw away the steam, turn the steam back in the water like I do here. I don't have the Missouri River flowing by. I have nothing out there to put the excess heat into. So what I do is I use a thermocouple arrangement to take the electricity out of the reactor. And I can run the reactor at several thousand degrees, assuming I have the right material made out of it, and I can use the thermocouples to remove the energy from the reactor. But I'm going to have thousands of them embedded in the reactor. So our science fiction, the Navy has such a reactor. We built it in the 50s. We never used it at sea. It was totally useless. But as a power supply for outer space, it would probably be a good idea. And so when we do that next. So we have a problem with space junk in near Earth orbit. The current thought is we make nuclear-powered space vehicles, unmanned, and all they are is tugs, and they go and move that stuff out of the near Earth orbit. Using one, we can get material from near Earth orbit to the moon in 200 days. Well, that should be okay, right? Unless I'm on the moon starving and I need something quickly. But assuming that I don't use all my water up on the moon, and I don't have to get it there soon, I can resupply the moon using a robotic system, nuclear powered, no men on board, moving things from near Earth orbit to the moon and back and forth. Every 200 days, 250 days, it can go one way. 250 days, it come back. Oh yeah, you'd have multiple of them up there, yes, at the same time. So if you had 200 up there, you'd have something showing up every other day. But anyway, my high temperature, my thermocouples, are the guys that are probably going to be the technology that I use first. There's other technologies that I'll use second. So here's my dissimilar metal at the heat source, creating voltage, going through an amp meter so I could measure it. Now we're just using the thermocouple as a sensor. We're not using thousands of them as a power supply. And we wouldn't. In normal commercial applications we wouldn't do that. So, but in an outer space application we probably would do it. That'd be a reasonable thing to do. On the Earth I have so many other things that I can do, like burn coal. I don't need to have some fancy way to do things. So I have some thermocouple, some block, some reference. I hook those things up. Precision, centigrade, temperature sensor. So LM35. I can buy one, I can put it in the circuit, I can make it work. Somewhere in the shop I have a heat sensor that you can point at people and see how hot they are, or an electronics part. So at the heat is the #1 enemy of anything electronics. So at the Rockwell Collins plant in Cedar Rapids, they have a shop about the size of this one, and all they do is measure the heat coming off the product that they make. Do we have a big enough heat sink? Do we have to arrange the parts on the board differently, printed circuit board differently, so to dissipate the heat better, so that these things last longer? We also use them in firefighting, and in finding out, so the place is all filled with smoke. Where do I spray my water? I'd like to spray my water on the fire. So if I had something that could detect where the heat source was, I know where to put my water, or where to find the person to bring them out, or as in yesterday, where to leave the person until the place burns to the ground, and then see if the body's there. So that was, yeah, no. You don't think that was him? You think that was some extra body? Yeah, yeah. I think, I think that I don't know. It all depends how smart he is. Yeah, but I would definitely have changed my hair, changed my skin color, done all kinds of cool things to stay hidden, and not allowed myself to be caught so quickly. I mean, gee whiz, I had years to plan this, and it only lasts for a week. I mean, really, talk about a loser. Anyway, so now we're into how do I sensor pressure? What do I do to decide that I have some pressure someplace? On a submarine, I have 20-pound air, 100-pound air, 150-pound air, 3,000-pound air, and 45,000-pound air. Clearly, I'm going to have some gauge to sense and tell me that I do. Right? So this board-on-tube thing is the thing I'm going to use. If I have any pressure above 100 pounds, I'm going to use something like that. As the pressure increases, the tube moves, and that little bit of movement, I throw some gears on and a arm on to measure what the pressure is. So that's how I do that. If I'm doing a little bit of pressure, I have a little bit of a diaphragm thing. I see a little bit of deflection in it. Again, I can put movement associated with that deflection so I can see what it is. I could have a billows arrangement, so the pressure goes up, this thing expands and gets bigger. I can use it to push some coil, some magnetic thing through some coil that changes the properties of my electrical circuit, so I can actually see a pressure change, voltage change due to that happening. So that's how I do that. So here we have, I'm trying to find a differential pressure. I have port 1, port 2, the diaphragm goes back and forth, and now I can measure the differential pressure. Clearly I'm going to have something attached to that diaphragm that's showing me that. Here we have the thing attached. So I've got some crystal hooked up to the diaphragm. When I take a crystal and I squeeze it, we have a thing called a piezoelectric effect. The piezoelectric effect gives me a voltage. So the voltage is going to change as the pressure changes, and I don't need a whole lot to a pressure change to see that piezoelectric effect. I was with the guy at Lewis Central, their Project Lead the Way guy. He had a sensor that could sense between 10 pounds of pressure and 5,000 pounds of pressure. And what he was doing is he was making things out of wood and then crushing them and seeing when they would break. Oh, that sounds like fun. Yeah. But he couldn't figure out the wires coming out of it to go to his amplifier, and that's why I was there. And it was just a matter of reading the manual and hooking it up the way it said to, which is what we do, right? That's what you do. You know, when in doubt, do what the manual says, right? Don't go running to your instructor wanting help, like certain guys. I won't mention Steve's name, but no. So here we have solid state pressure sensors by Motorola, and so now I can put the pressure sensor in some solid state thing, hook up some wires, be all happy about it. So I have some grid pattern.
Okay, so
All right, metal strain gauge. Okay, so I'm going to put something like that on my bridges and send it back to the DOT office to see, so it'll know when the bridge fails and 500 people fall in the Missouri River, they can say, oh yeah, we saw that last week and didn't do anything about it. Yeah, the same type of thing. So as my strain gauge force moves, the wires compress, the wires depress, and I end up seeing a voltage difference. So I have an active gauge and a dummy gauge. Oh well. Here we have a load cell, packed full of strain gauges. It can go up to 50,000 pounds. That should be enough in general. Maybe not. Not on a bridge. You're going to need several million pounds probably. This is a load cell bridge configuration. Wow, this looks sort of like what we had before, right? So my voltage from the load cell comes in, and I can tweak on things so that I get the gauge in the right spot, and I get some voltage out. Okay, now things flow in pipes. Okay, so they can flow in a laminar way, which means a uniform way through the pipe, very orderly. So if on my submarine, laminar flow is good, I like that. It could be ununiform, so I could be moving faster at the top end of the pipe as I do on the bottom end of the pipe. If I have some heat flowing into the pipe, I have heat on the outside of the pipe, I'm trying to get the heat in the water, then I'm going to want a turbulent flow. The turbulent flow is going faster, and what it's doing is, in a laminar flow situation, you can actually have the water boil on the pipe and not have any heat transfer. So and my heat transfer rate goes down because now I have steam coating my pipe as my flow is going down it. If I have a turbulent flow situation, then I'm taking that steam that's forming on the pipe and I'm removing it, and I'm putting it back into the liquid, the energy back in the liquid, and I'm more effective heating up the liquid. So on my submarine, I want to have turbulent flow going through the reactor plant. I don't want it to be a laminar flow type thing. And now we want to know how much flow we have. So I got some flow coming in. I've got some orifice plate that I put in there. Normally that's a little small, right? I'm not going to have much flow through the orifice plate. And then I'm going to have some pressure difference on either side of the orifice plate. And that difference in pressure is what I'm going to use to say what my flow is. So I have 1 pound difference, then I have 30 gallons per minute. If I have a 2 pound difference, I have 60 pounds per minute. Okay, so I put an orifice in, I go and that orifice just might be a Venturi thing, a thing that makes maybe the next picture. There we go. I got a Venturi. So I don't have an orifice in the way, I just make the pipe a little smaller between my two ports, and now I have a difference in pressure between those two ports, and that different, as I get more flow, I get more pressure difference. And so now I can go and do things like that. Now, is this going to work if I have pulverized coal going into the coal furnace at the coal power plant? Am I going to have some Venturi thingy restricting the flow so I can see difference in the pressures? And the answer is no way, Jose, right? Because as soon as I did something like that, this coal dust is going to clog up these ports. I mean, and they're going to be clogged up before I turn it on. I mean, that's going to be a non-starter. So at the coal plant, they got an 18-inch pipe feeding the pulverized. Is that 18 inches? 18-inch pipe. That's like that. That's right there. Yeah, that's 15 inches. This is more like 18. That might be 24. Anyway, they got an 18-inch pipe that takes. They have 24 different pulverizers that pulverize the coal and turns it into dust. You know, just the worst dust you could possibly have sitting on anything, right? So you don't want to have it out. And then they send it into the furnace through this 18-inch pipe, and they want to know the flow rate of the coal. And they do that with a cobalt 60 source. So they take cobalt 60, put it on one side of the flow rate, and then they measure the radiation on the other side, and that change in radiation, as the radiation changes, that's a change in the flow rate. So if there's no flow going on, a lot of radiation gets by. If there's huge amounts of flow going by, a lot of the radiation doesn't get by, and then they can measure the difference in the flow. Now, they have other things they can do too, because if they don't have enough flow of coal, then the furnace is getting colder, right? So they have other instrumentation that measure heat things. But if all I want to do is know the flow rate of something at 100 pounds psi flow type thing, I do a Venturi, and I do I look at the P1, P2. When you get in your physics class, there's a chapter on flow, and you'll actually do those calculations. Right now we don't, I don't think we're going to do those calculations in this class. I can also throw a tube in and to measure that difference. So if the flow's coming this way, I'm going to have more pressure on that side. If the flow's going that way, I'm going to have less pressure on that side. And as the flow changes, that differential will change, and I'll be able to get to the flow. I'm doing the same thing now with a nozzle. So instead of using a Venturi, I'm doing a nozzle thingy. If the flow rate here is 10 gallons per minute, what's the flow rate over here? 10 gallons a minute, right? What's the flow rate through the nozzle? 30 gallons a minute?
Yeah, 3 times.
Yeah, maybe 30 gallons a minute, right? Because whatever the flow rate on this side of the nozzle is, it has to be the same flow rate in the pipe on the other side, right? No water is leaking out someplace. But if this is only 1/3 the diameter, 1/3 the area, okay, so pi r squared, the area of the circle, right? So if this guy here is 6 and that guy there is 2, I'm going to have a huge flow rate going through the nozzle, but I'm still only going to have 10 gallons per minute on either side of that pipe. I'm just going to speed up through the nozzle, and that's going to cause a difference in pressure in port 1 and port 2. I'm going to use the fact that when my flow goes on an angle, I'm going to have faster flow on the shorter side of the elbow, slower flow on the top side of the elbow. That's going to be a pressure differential, which I'm going to be able to measure and use for that purpose as well, for flow. So I just throw something on there. Now this is cool. This is a paddle wheel thing. This is what is normally used in your house to measure the amount of water you're getting to, you're being paid for. So how often do you want the paddle wheel assembly replaced that measures the water going into your house? Never.
Not often.
Never, right? Because when's the only time that it's accurately measuring the amount of water going to your house?
When it's moving, yeah.
The day it was put in. From the day it was put in, it will gracefully decay. So I owned a house in Maine. The house in Maine had a 40 by 20 foot swimming pool. And in the winter we used X amount of water and we got charged for it. And in the summer we filled the swimming pool many times with water and we got charged the same X amount because that paddle wheel had been there for 30, 40 years and wasn't measuring squat. Okay? In Connecticut, they decided, oh, what we're going to do is we're going to go and change how we read our meters, and we're going to change out all the meters and make them RF. And now the guy can just drive by in his truck and query your RF water meter. Well, the day they did that, my water usage went up. It went up by a whole lot. So when you get your water bill, if you look at it, there's a fixed cost, right? And then there's a usage cost. And the fixed cost is $40 and the usage cost is 10. Now, why is that? Well, because they know they have to replace it. But that's why this water wheel thing is going to go and give you the right answer the day it's put in. And from then on, it's going to decay. And 30 years from now, it's not going to have any wheels left. So this is a paddle wheel type sensor. Here's another paddle wheel type sensor, but now I have vanes. But I'm doing the same thing. I'm making vanes go roundy roundy. Another flow sensor, small. But again, it's a Venturi thing, and my pipe goes down. A vortex flow sensor. So I throw in some body in there that creates turbulent flow and vortexes, and I'm detecting that. Yeah, go ahead, ask me how. Somebody ask me how.
How?
I have no idea how that works. Absolutely no clue. So here's a vortex flow sensor. You know, someone sold us a bill of goods. This guy is putting in a magnetic field, and the flow rate is going to change the magnetic field and change what the coil sees. So as I flow faster, the magnetic field characteristics are going to change. I'm going to be able to censor that. I'm going to be able to sense that. Electromagnetic flow sensor. I could probably get one of those for $500. That shouldn't be a problem. Another one looks cheaper to me. It's probably a $250 one. Now we're going to go with ultrasonic sensing. So I'm going to send in some sound wave, an ultrasonic sound wave, and it's going to reflect back through the water, and if the water goes faster, it's going to reflect back differently. And I'm going to sense that. Now, luckily, you were not in charge of creating the heavens and earth, so you were not in charge of making the ultrasound part work. All you do is just change the wires out and change the sensor out if it doesn't. And so now I've got a heater, and I'm sensing the flow by the change in temperature. Okay, so I got a little heater in there that's going to change the temperature by a little bit. If I have a little bit of flow, the temperature gets changed more. If I have a whole lot of flow, the temperature doesn't get changed very much. I measure that difference in temperature. I equate that to a flow. Who would have thought? Yeah, I've never seen one of these before. So I'm gonna twist my thing and see some flow. All right, whatever. I'm sure we do. Visual flow sensing. So it looks like that's what it says. I must put some camera in the middle of the fluid and watch it go by. Now I've got a float switch. Now our number one acquaintance with a float switch is on our toilets. And we replace them all the time, right? We go and replace that valve. But that's not really a switch, that's just a valve with a float on it. This is a float that has a valve associated with it. I have 6 of these floats, I have 6 of these valves. I just haven't bothered to build the wood thing so that you'd have to hook up some float switch. And quite frankly, you hook up one switch, you hooked them up them all, so I'm probably never going to bother doing it. But I did buy them at one time. Here's a float switch that goes up and down, so you have some sanitary tank that's filling up in the basement because the sewer pipe's higher than your basement, and when the tank gets filled, it starts pumping down. Works fine, lasts a long time, until somebody goes and throws an empty box on top of it, and now it overflows because it doesn't float anymore, right? Yeah, so if I go and I got something up here that's moving up and down. In '83, it rained in Connecticut every weekend for 5 weeks in a row. And at the end of the 5th week, the basements filled with water. The water tables raised and got above the basements, and the basements were filling with water. So I went and I put in a place for a sump pump, and I put in some PVC piping, about 50 feet of them, underneath the basement floor after I pounded it all out. What a pain. Never had water there before, again, so it was never an issue, but seemed like a good thing to do at the time. But you can do that. You can, if you're in Georgia, when you build a house, the lot normally has standing water on it. So the first thing you have to do is lower the water level of the property, and you do that by one of 2 ways. You either dig your drainage ditches deeper, or you add dirt to the top. So where Trident Trading Facility was, which was my last command in the Navy, before we built this 500,000 square feet building, if you were standing on that property, you would have been standing in 3 feet of standing water. So we added 6 feet of dirt to bring the dirt level up, and then we put a 4-foot cement basement, 4 foot of cement for its basement on top of that, and then we built a building on top of it, and we're okay. So you can do that. So here's my float switch going up and down, and I have multiple sensors going to sensor its position. So I'm either there, here, 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 and I have lights going on and off as I go up. So I have a low level alarm, I have a high level alarm, and I have a normal operating position type alarm going on. Here I've got a level sensor, water goes up. I have some magnetic sensing switches. I'm low, I'm a high. I got a vibrating rod. So my vibrating rod's vibrating, everything's fine. The water gets up to it, It doesn't vibrate as good. I know the level's too high. Vibrating rod sensor. I have some optical type sensor. So I have some light path, I have some prism, the water gets too high, it doesn't follow that light path anymore, and I know the water's too high. I have 2 electrodes. When the water gets too high, now I have continuity through the water and I know I'm there. Pressure differential. So now I'm measuring the pressure that the liquid's giving me, and I'm using that to tell you what the level is. I have a capacitor sensor. So I have the capacitance of the sensor will change when the water gets there. Oh, yeah, I guess it will. So here's a bunch of level detectors. Ultrasonic level detector. So I send sound waves down, I get them back, and I use how long it takes them to get there and get back. So it's sort of like sonar. When my depth finding on my submarine, I turn on my sonar. We normally, on a submarine, you normally don't have your sonar on, because if you do, somebody might hear you, and that'd be bad. But as soon as you surface the ship, then you turn on your depth finders, so you keep track of your depth when you're on the surface. You normally submerge after the 100 fathom curve, which is more than 600 feet of water, so you really don't care. You know, you look at the Atlantic Ocean, and only 5% of the area of the Atlantic Ocean is shallow enough for the submarine to be sitting on and not be destroyed. So once you get out in the ocean, there's so much water that you don't worry about it anymore. But we do bottom contour navigation. So during the height of the Cold War, we had parts of the ocean that we had taken very precise measurements of the bottom. And if you took your submarine across those spots, you could actually fix your location within inches on the globe. So we had the technology to do that, and those are sonar type things. So here I have a level sensor where the water is just bringing up the spool and letting it come up and letting me measure it. Water level sounder. So you stick it in the tank and ask it how deep it is. Then there's the old stick the hunk of wood in the gas tank at the gas station to see what the level is in the gas tank. You have that too, right? You just don't have any electrical sensors going by. Yeah. And you can tell how much water is in the tank and things like that. This is a linear sensor, so my position arm is going back and forth, and I'm changing my resistance. So I have a wiper that's going back and forth, changing my resistance, just like a potentiometer would do. So that'd be a linear potentiometer position sensor. Now I've got a rotating thing, so I'm rotating on the same type of thing. So as I move my rotation, I change the resistance between T1 and T2. I have linear variable differential detectors. So here I go and I have some voltage in, and then I have voltage out, and depending on where my movable core is will depend on what my signals look like. So if I'm over on this side, I'm in phase all the way. If I'm over on the other side, I'm 180 degrees out of phase, and if I'm in the middle, I'm out of phase on A, but not out of phase on B. So I can go and decide where that movable core is going back and forth between the A position and the B position, depending on the changes in phase between my input and my output. A more complicated thing to measure, but we're just electronic guys, right? That'd be perfectly okay with us to see some phase difference. Humidity detector. Oh, platinum, I like that. So I have a capacitance sensor thing As the humidity changes, the capacitance changes. And I can now sense humidity. Oh, this looks like problem number 1. Oh, time for problem number 1, I guess. What problems do I have to do? Oh, I have to do problem number 1. All right. Did I bother to? Yeah, I did. Well, that certainly is big enough, isn't it?
That's 390 something.
Number 1. Okay, so in chapter 7. I made it to chapter 8 already. Chapter 7 problem. Okay, 397, I agree. Page 397. Analyze the figure below and describe the operation of the four-way, four-port, 2-position solenoid valve for de-energized and energized. So I'm in the, would appear that I'm in the energized position now. So I have, that would be in. That would go to my piston probably. So there's my piston. So that's going to my piston, and then coming out of my piston I would go into there, and then this would go to the vent and supply tank. Okay, and then I'd energize it, and now oil would go into 1, my oil would go on this side. This guy would move over to there, and then go to the vent and supply tank on the other side. So in one direction I'm pushing the oil that way, pushing it out. In the other way I'm pushing it in, pushing the piston that way, pushing it out. Well, that was enough BS, right? Good thing we have mechanical eyes. Number 3. You ready?
Not really.
Want me to put some more color up there?
Sure.
Yeah, sure. That just mess up the picture. And then it's a 4-position guy, so it could go either way. I could. Each of these ports would have to have a hole stuck, a pipe stuck in them, or a plug stuck in them, so it doesn't do whatever it does. And it's not showing the pilot side, so just the way it is. All right, looking at number 3. What is the thermal capacitance of turpentine flowing at 0.002 meters cubed per minute? And we're having some slight technical problems here. All right, so 0.002 meters cubed per minute. Is that a lot? That's like 2 liters, right? 2 liters a minute? That's not very much. When its density, all right, so the density is 870 kilograms per meter squared, meter cubed. Okay. so that's the now what's the density of water? Regular tap water is 1,000 kilograms per meter cube. So this is something that's less dense than water.
Less than water.
And the heat capacity, yeah, like basically, don't drink it though. 7.21702 joules per kilogram degrees centigrade. Now I know absolutely nothing about anything except what the problem gave me, right? And what I want to do, I want to get an answer. Now, when you get to Physics 2, then, which is your last semester here, heat flow is something that's there, and that's what you do. So, but now we got to do this without knowing anything. What is the thermal capacity of turpentine? All right, so thermal capacity would probably be joules per kilogram. Is what I think is joules per kilogram degree centigrade. Yeah, I'm pretty sure it's joules. What we do when we're talking about only units, we put brackets around. So the thing we're looking for is joules per kilogram degree centigrade, and but that's what we have here. So the heat capacity, what is the thermal capacitance? Thermal capacitance. Darn, now we're going to have to look in the book and see what thermal capacitance is. But sure I could solve it without it. All right, thermal capacitance. I'm sure that somewhere, someplace. Oh, there we go. Thermal capacitance, page 346. So, page 346. And thermal capacitance is density times volume times heat capacity. All right, now, when you get to your physics class, that's going to be
Is that a P?
density, volume, little c is going to be the heat capacity. So they're using, this author's doing something weird. But anyway, the bottom line is all we have to do is multiply those guys together. 0.002 meters cubed per minute times 870 kilograms per meter cubed times 1720 joules per kilogram degree centigrade. So all we're going to do, we have three things, we're going to multiply them together.
Can you fix that? The first term, it says 002 and 3, and then what's the slash, and then what?
I don't know. That was a long time ago. You want precision in my work? No, I get precision in your work. I don't need precision in my work. All right, so I got meters cubed on the top. I have meters cubed on the bottom. I have kilograms on the top. I have kilograms on the bottom. Okay, so when I get done, I should have an answer. Whatever that answer is should be in joules per degree centigrade minute. Right, because I have a degree centigrade over here, don't I? Yeah, right there, degree centigrade that I can't see because it's stuck over there. I would have corrected that, but Raimondo didn't ask me to correct that, so I didn't. All right, now, can I do this in my head? Or do I have to rely on my calculator? And will my calculator work up here with the bad lighting? You know, those are all issues. So the first thing we do in industrial electronics when given three numbers is multiply them together. If that's not the right answer, then we don't care. 0.003 times 870. Oh, you don't have that many significant digits.
Four.
2992.8. So I think that rounds off to 3K. What do you think, 3K? We'll go with 3K joules per degree centigrade minute. And that would be our heat capacity. Well, isn't that good? Yes, I think so. I hope the other ones are that easy. Number 5. Number 5. Oh, yeah, no problem. 20 degrees centigrade equals, no, 20 degrees Fahrenheit. 20 degrees Fahrenheit equals what in degrees centigrade? Well, your calculator had better do that for you, right? Because otherwise you're going to have to remember some formula. So 20, third section function convert temperature, and I want to go Fahrenheit to centigrade. Boom, boom. The answer is minus 6.6 repeating. Okay, so if you can make your calculator do that.
You did it on the calculator. Can you write it down, please?
What calculator are you using?
Expro.
Alright. So you're going to go 20, second function, convert, temperature, degrees Fahrenheit to degrees centigrade, enter, enter. All right, so can you make it do that?
Thank you.
All right. Now, this of course has to be a teaching moment, right? So I can't do that. How am I going to figure it out? All right. So we start with something we know. Where does water freeze?
32.
32 degrees Fahrenheit. Where does water boil?
112.
212 degrees Fahrenheit. Where does water freeze in centigrade? 0 degrees centigrade. Where does water freeze in centigrade?
Boils?
Where does water boil in centigrade? 100 degrees centigrade. Okay, so there's a change here between that side and this side, right? So what is 100 divided by 212 minus 32? Minus 32. All right. And that's going to be 9/5. No, it's not. It's going to be 5/9. 5/9. Is that not so? 100 divided by parentheses. 212 minus 32. Boom. And I have 0.55 repeating. Okay, I'm going to second function change it to a fraction 5/9. So this is
Is it 12 minus 32 degrees?
112 minus 32. So I look at the difference here, 112 minus 32, and I look at the difference there, 100, and I see that a degree Fahrenheit is 5/9. So of a degree centigrade. So this is degree centigrade per degree Fahrenheit. So that's the difference between those two. All right, so I got that one figured out because I have my calculator, and I remember where water freezes and where water boils. If I don't remember those things, then I'm hosed, and I better have a calculator that does it. Okay. Now, so that being the case, I know degrees Fahrenheit. I know it, and I want to go to degrees centigrade. What am I going to do? Well, I'm going to take that degrees Fahrenheit, whatever it is, I'm going to subtract 32 from it, and then I'm going to multiply it by 5/9, and I'm going to get degrees centigrade. Okay, so that's what I'm going to do up here. I've got 20, so I'm going to take 20, I'm going to subtract 32 from it, and I'm going to get minus 12, and then I'm going to multiply that times 5/9, and I'm going to get minus 23rd degrees centigrade, and then I'm going to take that, I'm going to change it to a decimal number, and I'm going to get minus 6.6 repeating degrees centigrade. Exactly what my calculator told me it was before I went through all that. Okay, so now I've got degrees centigrade, and I want to go to degrees Fahrenheit. What am I going to do? Well, I'm going to take whatever my degrees centigrade is, and I'm going to multiply it by 9/5, because a degree centigrade's worth more than degrees Fahrenheit. And then when I get done, I'm going to add 32 to it, and that's going to give me my degrees Fahrenheit back. Okay, now, at what temperature is my degrees centigrade equal to my degrees Fahrenheit? What temperature does that occur? Okay, you knew that where water boiled, you knew where water froze, right? So you also know what temperature is the same for centigrade and Fahrenheit. I know it's there. You had it in 8th grade. What is that number, Steve?
5.
No. Minus 40. So at minus 40 degrees, my Fahrenheit and my Celsius are the same number. So that means if I take minus 40 degrees in my calculator, minus 40, and I multiply it times 9/5, and I add 32 to it, and I add 32 to it, I better get minus 40 back, and I do. Right? And if I take minus 40, minus 32, and I multiply that times 5/9, I better get minus 40 back, and I do. So you don't have your calculator, you're stuck in the desert, and you have centigrade, you have Fahrenheit. Now you know how to do it without a convert thing on your calculator. I prefer you to have a calculator that just does it, so you get the right answer. But that's how you get those numbers. You look at where water freezes, where it does the other thing, right? Okay, good enough? Right. So we derived from first formulas. Now we're looking at number 12.
You know how to do it on TI-84?
No. I wish I did, but I don't own a TI-84. It has to do it though, and it's probably under units, maybe. Right, I'm doing number 12. And that's something that you should have done in 8th grade science class, that Fahrenheit or whatever. Describe the flow rate if the turbine flow sensor has a K factor
Number 12?
Yeah, has a K factor of 11 centimeters cubed and 760 pulses were counted during a period of 1.250 seconds. All right, do you want the real answer, or do you want me to just mess with it? Okay, so the flow rate. Okay, so flow rate would be in centimeters cubed per second. So that's what I'm looking for. So I imagine that if K is 11 centimeters cubed, then I'm going to have 11 centimeters cubed per pulse times 760 pulses divided by, because I need it to be per second, right? 1.25 seconds. And that's going to give me a flow rate. Yeah, Q is my flow rate. Flow rate, and it's going to be in centimeters cubed per second. All right, so I'm going to go and take 11 times 760 divided by 1.25, and I'm going to get 6688 centimeters cubed per second. And then I'm going to ask myself, how many significant digits can I possibly have? And I probably have 2. So I'm going to say my flow rate is going to be 6,700 centimeters cubed per second. Or I could change it to meters cubed. Would I want to do that?
No.
Okay, so if I wanted to do that, I'd have to say that in 1 meter cubed, there are 100 centimeters, 10 centimeters, 10 centimeters cubed. No, I was right the first time. 100. So there's 100 centimeters per meter. So 1 meter cubed is going to be 100 centimeters cubed. So this is 10 squared 10 to the 6. So I move the decimal point 1, 2, 3, 4, 5, 6 places. 0.0067 meters cubed per second. I like my answer in centimeters cubed better. That looks nicer. But I could change it if I wanted to. Well, I did change it, but I didn't. I don't want to, so I won't. 15. What is the specific gravity of 1 cubic foot of tomato paste that has a mass of 55 pounds, 55 pounds at 20 degrees centigrade? Okay, so specific gravity. Well, guess I'll have to go look. I know I knew that at one time.
It's 25 degrees Celsius, by the way.
What?
25 what?
So, what's
55 what?
pounds? Somehow I don't think it matters what temperature it's at, but I'm not so sure about that. So now we have to find where the tomato paste was here. Okay, so there we go. Specific gravity on page 390. So I'll go to page 390. And the specific gravity is going to be the density of the liquid divided by the density of water. Okay, so the density of the liquid is going to be 1 cubic foot. No, it's not. It's going to be 55 pounds. 55 pounds per cubic foot. And water, what is the weight of 1 cubic foot of water? Cubic foot of water. You don't know that? Shit. 62.4 pounds. Everybody knows. You got a gallon of water, right? And you're picking it up, and anyway. But everybody knows 62.4 pounds per cubic foot, right? Do you know that? All right, maybe you don't. Now you do. Well, I'm looking at page 390. That's how I know it. I thought it was 62, but I didn't know it was 62.4. All right, so the specific gravity of the tomato paste. 55. The next test is going to be cool, I can tell. 55 divided by 62.4 equals. And I only have 2 significant digits, so I'll go with 0.088. Oh, we are now done with that. Chapter 8 is safety. And during the safety lecture, Steve will not have to be here. Well, one of the Steves won't have to be here. Because it all has to do with robotic safety, and he's already had to put
So
up
there's
with
no
that one.
units on the .88?
What?
There's no units?
Specific gravity has no units. Never. And if I look at this formula, and I use my red pen, I see that the pounds cancel, the cubic feet cancel. Specific
where he
gravity
corrected in that,
is
remember?
unitless.
That's where Miss Hamilton was correct.
She was correct once
She was corrected
today.
Corrected.
by you.
That's right. That's where I corrected her. Right when she tried to give you the wrong.
She tried
units.
to hose us.
Oh,
Yeah,
she
tried
did.
on purpose to hose you. Yeah. Well, I pay her extra for that.